Hi everyone, welcome. Hope everybody is doing great. Uh, I'm back with another tutorial after a very long time, and this tutorial is actually a request that I found in comment section by a subscriber. So I will dedicate a little bit time to demonstrate you about the molecular dynamic simulations, the ab initio molecular dynamic simulations using the DFT codes. And in this demonstration I will use VASP, Siesta, but you can even use this idea in quantum espresso, castave, and so on, because the idea of all DFT code is almost same, only the flavor a little bit different. Okay, so let's just start with this figure, and this figure is actually from a paper, actually my paper that published in back in 2022, and there we introduced a new material, and a totally new material with a lot of testing. We test the chemical stability, cohesive energy, formation energy, so on. We see the phonodynamics, and of course for the experimental synthesis it's very crucial to see the molecular dynamic simulation. So that's what I'm going to talk about today. So let me show you the figure in a big scale. So yeah, here in this work I have shown this particular material stability in different temperature. First I simulate this system at 300 Kelvin, and then I did it for 1000 Kelvin, and a lot of information we can see in this figure, but the important thing that we see is the geometry. First, the geometry we can see is not broken. The bonds are almost intact, not melted at 300 Kelvin, and we can say it's stable. One thing. Another thing is, like, you can see the energy. The energy is almost linear. There is not a drastic fluctuation or elevation. So we can say this is stable at 300 Kelvin temperature. And you can see with the red curve here, it means I subject this material at 1000 Kelvin, and now you can see the energy is slightly increased up, because now minimum energy is not like 300 Kelvin, it's grown, and the system is a little bit now deformed. You can see the bonds are a little bit trying to break, but still they are stable, I can say, because as I said before, this energy is still linear. So this is a basic information from this molecular dynamic simulation, which is describing that this material is stable at room temperature and beyond that, even up to 1000 Kelvin. So this is what we can claim with the help of molecular dynamics. And mainly you can use ab initio, which is quite accurate, predicting this kind of stability issues. But if you want to do other thing, like if you want to go with biological simulation, like the molecular docking and protein study and so on, you can go with other classical molecular dynamics like GROMACS, NAMD, and so on. Games, yeah, a lot of things are there, but in this video I will be focusing on ab initio molecular dynamic simulations. Okay, so what is molecular dynamic simulation? I think you already know basic idea of molecular dynamic simulation. It is nothing but the observance of system evolution when it is subjected in certain temperature, pressure, and certain volume condition. So generally these parameters in molecular dynamics are called the ensemble. Generally there are these various type of ensemble. One is microcanonical, the canonical, isobaric-isothermal, and so on. And to achieve these temperature and pressures constant, you have to provide the system certain Boltzmann velocities, and we call it thermalizing the system. So this thermalization can be done with different algorithm that is developed by great people there in mathematician. The idea of this can be written here in different algorithm, that is Anderson, Nose, Langevin, and multiple Anderson, and so on. So these are the thermostat, and these are the ensemble. So in ab initio molecular dynamics, even in classical, you need two things to remember in molecular dynamics simulation. One is the ensemble, and there is thermostat. So as I mentioned here, this is done in NBT ensemble because here temperature is fixed and energy is evolved here. Energy is allowed to freely move and see the fluctuation. So this is NBT ensemble here. So I will just demonstrate about the NBT ensemble, but you can even try with the other ensemble with the same idea. So let's start with practical demonstration. So here in this practical demonstration, I will show you beyond this this figure. I will demonstrate today the how we can see the mean square displacement, how we will see the diffusion of the material, as well as I will show you the system evolution trajectory, and I will also demonstrate the average temperature and pressures curve and so on. So let's begin. So these are the input needed in VASP calculation, and most important thing that we need to know is these flags. I will mostly focus here on this flag. The first thing is like the NSW. This gives you the simulation length. So it depends on how long you want to simulate the structure. For example, here I simulate the structure up to 10,000 femtosecond. So if you want to go with 10,000 femtosecond, just make it for 10,000. And POTIM, this is actually the drift energy that that system needs to achieve this particular temperature. So this is actually the potential, you can say. So the value can be ranging from 0.5 to 3, 4, but you can start with 1.0. This is sufficiently enough to deal with almost all type of system. And this is the target temperature. So as I saw here, so room temperature is around like 300 Kelvin. So you can go with 300 Kelvin and see what happens. And this is ending temperature. So temperature and ending and beginning temperature is the same. So it means temperature is constant. So this is NBT, and the N block is like the command that will allow you to allow the code to write the system evolution in x.car file. And s mass equal to 0, this is actually the thermostat that I was talking, and s mass equal to 0, this will give the code to use Nose algorithm. So you can read more on this documentation, but this is what I'm using here right now. Okay, so hope you all understand, and any confusion you can write in comment. And before I just move into more discussion here, I would like to request you to subscribe the channel if you are new, because I'm aiming to have subscriber like 1,000, and that helps me to reach with more people, and helps me to keep motivating to make other video. Okay, hope you will do that. So let's start with the calculation. So I have already performed the calculation quickly, so the results are here. So this is the result at 300 Kelvin, and let me see the output. So there are a lot of output here, but the main important output that you need to take here is I'm going to explain here. Okay, so don't worry about this data. You will not find this data in your fresh output of your molecular dynamics simulation. This is actually I tried before I demonstrate here. So these are the output that you don't need to worry. You will not find this thing there. So here the important thing you need to take here is the VASP.xml. This is very important file that stores almost all the information needed of your system. So you need to take a look on this file with different third-party software. You can even visualize this. And another thing is x.char. This file will store the system evolution, and we can see that using certain program that I will explain. And important thing is this current. This will show you the final result, how the structure appeared after that 300 Kelvin temperature. And the OCCAR file, this is a really important file. This file contains the evolution of the energy, temperature, pressure, free energy, so on. So these are the file, and of course the outcar, because this will show you the temperature and the pressure evolution. So these things are really important to see. So now let's see how a structure appeared after the final result. So you can see similar result like I have plot here. You can observe with any visualizing software. I will use AASE because it is quite light and you can see the structure clearly. So let me see the bond. So yeah, I can see the structure is okay. There is no deformation, and you can see it looks okay. This is just a quick rough calculation, so I will not go in a precise accuracy, but I can say this is stable. But still I cannot say just observing the structural geometry, but I can confirm this with the energy fluctuation. So let me see the energy fluctuation now. So to see the energy fluctuation, you need to go to the OCCAR file. So a lot of things are here, but you don't need to see all this SCF evolution. You just need to see the temperature and energy relation. So for that you need to grep little bit information and remove the unnecessary information. So you can grab the temperature and energy relation with this command from the OCCAR file. So let me save it as md.dat. Okay, so this writes the temperature energy relation only. So let me just visualize the file md.dat. So let me just make the font a little bit smaller. Okay, so you can see the first column here, temperature, and then energy, and then free energy, and so on. So let me see the energy evolution. So here for this calculation I just performed only 1916 steps, so no worries, you may not find a really nice evolution, but it is sufficient for this demonstration, I believe. So let me plot this with XMGRACE. Okay, let me import the data, and this is set of log data. So where is that md.out? Capital MD it was. Yeah, here is it. So this is 1 and 3, so I have to do like this. Okay, so looks okay, not so bad, I think, because this is so rough calculation, so I should not expect yeah, let me just color it. Okay, can do with the decoration thing, so no issues. So let me go with my paper here, and in fact I would humbly request you, if you using this idea, then you can cite my paper and your work. Okay, so you can see the structure, sorry, the energy evolution is quite linear. Don't worry about this beginning shifting. Actually, this the early big fluctuation is just because the thermostat is just trying to push the system in 300 Kelvin. So no worries with that. So here you can see the structure is stable because the energy evolution is almost linear. You can see the energy is very much linear, and of course you can see the structure is stable at 300 Kelvin. Okay, so you would like to see whether the system is solid or liquid, or maybe something else. Okay, I think that may be really important to see. So for that you need to see the mean square deviation or displacement, mean square displacement. So for that you just need to go with the code, and I have this code, and if you're interested then I will provide you the code. So here I have already run the output, and I can see the output here in msd.out. This will give you the output result of mean square displacement. So let me plot the mean square displacement. Alright, so this is the mean square displacement, not so bad for this short simulation. So as you can see, the mean square displacement or fluctuation is not so bad. It's linear, you can see. So you can say this is solid. If the fluctuation was growing like this, and then going like this, means like going from 0, 0.5, 0.2 and so on, is in exponential ratio, then you should confirm that this is liquid. So I can say this is totally solid. So I can conclude here already that the system that we are working with is stable at 300 Kelvin, and it has stable energy fluctuations, and the geometry is stable, it's not broken, and a lot of things. So now you can even check the average temperature. So this is the average temperature. You can see the temperature is 300 Kelvin, not much different. As we ordered, we just constrain this code to run the simulation in 300, so result is also 300. So the calculation is going good. So yeah, now okay, so final thing is like we may be interested to see the evolution, how the system is evolved. So for that we can use this code Obito, and if you need some help with installing Obito or any information, I can help you with that. So I can see the system evolution here from the Obito. So here Obito shows the system here. Now this is the initial state. Now let me just see the system evolution. System is evolving like this. So you can see the bonds are a little bit moving, sorry, the atoms are moving, and it's still not so broken. You can say it's not so broken, not so much scattered structure. So this is how the system is evolved. The system is not so complicated, it is not so fancy, so you didn't see any kind of drastic change, but still the system is evolving. So you can see and visualize the system evolution also with the help of this code. Okay, so I think we are almost done with this molecular dynamics simulation thing, and now final thing is like maybe I will show you what happens at 1000 Kelvin. Let me just show you the result in 1000 Kelvin. Maybe this is for 1000 Kelvin. Let me see. Yeah, this is for 1000 Kelvin. So what happens to the 1000 Kelvin? 1000 Kelvin is quite high temperature. So what happened to the system? Let me see. The system is okay. I think the system is good. So so not be broken, but it's nice to see. Yeah, I think the system is not so good. You can see it's a little bit bended. You can see here. Yeah, not so well, not so okay. It's bended. You can see here, but not much because this system is good. This is highly stable system, so this is okay. So this is how we can go with this molecular dynamics thing. And if you're interested in other simulation like NPH or NBE, you can just change the parameter from your manual and you can do that. So this is for VASP. Now let me go to Siesta, which is one of my favorite code. In fact, I use Siesta in this calculation, and I highly recommend to use Siesta code because this is really fast code, and as compared to any other code that I experience. So a lot of output is here, but I would like to show you how we can see the system evolution and other things. So here and this okay, maybe I will go with the input. So this is the input file. This is the input file, and these are the important tag that we need to apply in Siesta input for molecular dynamic simulation. So Siesta is quite easy. You can see everything is clear. The type of run is nose. So as I said, this is a very important thermostat, and the temperature, the beginning temperature is 600, final temperature is also 600, and the time step is 20. This is the POTIM value that I discussed before, and this is the time step that you evolve. And you can even control the nose value here with these parameters. Okay, so now you can see how the system evolved here. This is the OSZICAR file. You can see, as I discussed in past tutorial, this is for Siesta, and in Siesta you will find this result similar to this OSZICAR file on the file MDE. So you can see this is a little bit short. I think I have another a little bit longer run. Just a moment. It should be here. Yeah. So yeah, this is the result for 15 femtosecond of simulation. So this is quite small because I did this in my laptop. You can see how fast the code Siesta is. Let me show you how big is the system and how fast the calculation is. So I have this laptop with 16 cores, so I will not use 16, I will use 12. What was the input file? You can see this tutorial is getting a little bit longer, but hope you will enjoy it. Yeah. Okay, so yeah, this is the input. Okay. What's wrong here? Oh, Siesta. Oh, sorry. I was stupid here. Okay, look at this. The code is not so bad. This system is composed of, I think, more than 200 atoms. Not this. Okay, this is just with only 80. Okay, I even try with 200 number of atoms, and the calculation was still fine. It was running good. You can see here the first step is already moving forward. So you can try with even with Siesta, because this is the open SS code, and you can go with Siesta also. You can give a try with this one. So okay, I will not wait for this calculation because the idea is almost same, the result will be almost similar there. So hope you all enjoy with this tutorial, and as I mentioned before, your subscription will help me a lot, so don't hesitate to do that. So thank you very much. And if you want to learn anything else that you are curious to learn, and you can write that in comment. I will come back with that in another video. Okay, thank you very much.